Hi everyone, let me introduce myself. My name is Jonathan Songgigilan, my student number 221011030049. I am a student in the math department at Sam Ratchalangi University. And now I will summarize the presentation of Professor Seiya Negami. But before that, I will introduce who Professor Seiya Negami is. Seiya Negami is Professor in Honor and Doctor of Science Topological Graph Theory, Math Education Yokohama National University Yokohama, Japan. Seiya Negami, born in 1957. He was graduated in Tokyo Institute of Technology. He was Dean of Faculty of Environment and Information Sciences from 2014 to 2018 and working as Executive Director and Vice President for Education and Publicity from 2019 to 2020 in Yokohama National University. He is a mathematician which is a pioneer of topological graph theory in Japan and working for reformation of mathematics education. Well, that's a brief introduction to Professor Seiya Negami that I can convey. And now is the result of the material summary. The title is Graph Covering and Their Applications, with the theme, Data Optimization for Instrumentation Physics, Food Security, and Energy Sustainability. How about AI? Graph covering and their applications. Graph covering is a mapping from one graph called the base graph to another graph called the covering graph in a way that preserves certain structural properties. The goal is to find a covering that satisfies specific criteria or constraints. Graph coverings are a fundamental concept in graph theory with various applications in computer science, network, design, and other fields. Here are some applications of graph covering. Network design. Graph coverings can be used to design efficient and fault-tolerant communication networks. For example, finding a covering of a network can help ensure redundancy and reliability. Coding theory. Covering graphs are used in error-correcting codes where vertices represent code words and edges correspond to potential errors. Finding coverings can aid in error detection and correction. Topology and geometry. Covering spaces in algebraic topology provide insights into the structure of topological spaces. For example, the universal covering space helps understand the fundamental group of a space. Parallel computing. Graph coverings can be used to model and optimize parallel algorithms. They help distribute tasks across processors while minimizing communication overhead. Cryptography. In some cryptographic protocols, graph coverings are employed to distribute secret keys securely among multiple parties. In summary, graph coverings are a versatile concept in graph theory with applications spanning multiple domains including network design, coding theory, topology, parallel computing, and cryptography. Artificial intelligence (AI) plays a crucial role in optimizing data for various applications including instrumentation physics, food security, and energy sustainability. Here's how AI can contribute to data optimization in each of these fields: instrumentation physics, data analysis, signal processing, predictive analytics, energy sustainability, smart grids, energy management, and renewable energy. In all these fields, AI can help optimize data by handling big data. AI can process and analyze vast amounts of data, quickly identifying trends and insights that might be challenging for humans to uncover. Automation. AI can automate data collection, cleaning, and pre-processing tasks, reducing the time and effort required to prepare data for analysis, prediction, and optimization. That's why AI is a powerful tool for data optimization in instrumentation physics, food security, and energy sustainability, enabling more informed and efficient decision-making in these critical areas. A finite planar covering typically means that you can cover the vertices and edges of the graph with a finite number of planar graphs without specifying how many times each edge is covered. Twofold planar covering would imply that each edge of the graph is covered exactly twice, which is a stricter requirement than a finite planar covering. It's possible for a connected graph to have a finite planar covering without having a twofold planar covering, and it's also possible for a connected graph to have a twofold planar covering without having a finite planar covering. Okay, that's all I got from the presentation. Thanks for watching. And now I'll show you behind the scene on how I made the avatar and voice over animation. Hi everyone, let me introduce myself. My name is John. Artificial intelligence plays a crucial role in Hi everyone, let me introduce myself. My name is John Songgigilan. My student number 22101103009. I'm a student in the math department at Education Yokohama National University. Logical graph theory, math education Yokohama National University. Sam Rajalangi University. And now I will summarize the presentation of Professor Seiya Negami. But before that, I will introduce who Professor Seiya Negami is. Seiya Negami is Professor of Honor and Doctor of Science, Logical Graph Theory, math education Yokohama National University, Yokohama, Japan. Seiya Negami, born in 1957. He was graduated in Tokyo Institute of Technology. He was in the Faculty of Environment and Information Sciences from 2014 to 2018 and working as Executive Director and Vice President for Education, Architecture and Correction, Topology and Geometry, covering spaces in algebraic topology, providing insights into the structure of artificial intelligence AI plays a crucial role in optimizing. Artificial intelligence AI plays a crucial role in optimizing data for various applications, including instrumentation. Okay, that's all I got for the presentation. Thanks for watching. And now I'll show you behind the scene how I made the avatar in voice over animation.